Now, let's have a solution to systems of linear equation. So this is now not limited to homogeneous system of equation. So we're going to extend it to non-homogeneous linear equation. So if x sub b is a particular solution of the non-homogeneous system ax is equal to b, then every solution of this system can be written in the form x equal to the particular solution plus x sub h, which is the solution to the corresponding homogeneous system. So particular solution, this is particular for the constant b, and x sub h would be your homogeneous system solution. You would be seeing this, you would be using this for your differential equations. So, find the set of all solution vectors of the systems of linear equation x1 minus 2x3 plus x4 equals 5, 3x1 plus x2 minus 5x3 is equal to 8, and x1 plus 2x2 minus 5x4 is equal to negative 9. So what do we do with these systems of equation? We first augment the matrix as 1, 2, 3, and 1. We find the augmented form of the matrix 0, 1, 2, negative 2, negative 5, 0, 1, 0, negative 5, and 5, 8, negative 9. So this is the augmented form of the matrix. From this augmented form of the matrix, we're going to find the row echelon form. From the given matrix, row echelon form. Again, the solution will be provided as an attachment to the class. So the systems of linear equation corresponding to the reduced row echelon form of the matrix is, so the matrices, the vectors that form a basis would be the first two rows. So we can have x1, so this is x1, x2, x3, x4, and then the constant. So that would be x1 minus 2x3 plus x4 equals 5, and x2 plus x3 minus 3x4 minus 7. So we can find the solution to this one by setting this one to be x1 and x2 respectively. So we can have x1 to be equal to 2x3 minus x4 plus 5. And then we have x2 is equal to negative x3 plus 3x4 minus 7. The given system would yield 5 plus 2s minus t, negative 7 minus s plus 3t, 0 plus s plus 0t, 0 plus 0s plus t. For the x particular, we have 5, negative 7, 0, 0. And for the homogeneous system, x sub h, we have 2, negative 1, 1, 0 s, negative 1, 3, 0, 1 t. So xp is the particular solution of ax equal to b, and xh is equal to s times vector u1 plus t vector u2, representing the arbitrarily vector in the solution space of ax equal to 0. Some properties. The system ax equal to b is consistent if and only if b is in the column space of A. So it is only consistent if B must be in the column space of A. If B does not belong to the column space of A, then if B does not define the column space of A, so it is not a solution to this. There's no solution to the system. So let us just consider this systems of equation. x1 plus x2 minus x3 equal to negative 1. x1 plus x3 is equal to 3. And 3x1 plus 2x2 minus x3 is equal to negative 9. In its augmented form, So we have 1, 1, 3, 1, 0, 2, -1, 1, -1, and -1, 3, and this should be -9. If we're going to convert this into its row echelon form, we are going to notice that B is equal to 2A1 minus 2A2 plus A3. So B, this column, is equal to 2 minus 2 plus A. So 2 times 1 minus 2 times 1 plus -1. So 2 minus 2 is 0 minus 1, so that's -1. 2 times 1 is 2 minus 0, so that's 2 minus 0 plus 1. So 2 plus 1 is 3. Now for the third one, 2 times 3 is 6. 6 minus 2 times 2, so 3 times 2 minus 2 times 2 minus 1 times 1. So 3 minus 6 minus 4. 6 minus 4 is 2. 2 minus 1 is 1. Okay, so this should be 1. This should be, let's correct this one. So this should be 1. So we can say that B is 2A1 minus 2A2 plus A3. So B belongs to the space spanned by A. So therefore, the system of linear equation is consistent. To summarize everything that we have learned so far, we are going to have the non-singular equivalences. If A is an n by n matrix, then the conditions below are equivalent. So if it is non-singular, a matrix which is non-singular is invertible. It has an inverse. So singular matrices do not have an inverse. So if we have an invertible matrix A, AX is equal to B has a unique solution for any n by 1 matrix B. Since it is non-singular, so A inverse exists. So if you're going to apply AX is equal to B, so you have X is equal to A inverse times B. So there is a solution. Now AX is equal to 0 has only trivial solution because upon the application of A inverse to both sides of the equation, so A inverse times the 0 vector is a 0 vector. So the only solution is the trivial solution. A is a row equivalent of the identity matrix of size n. A is not equal to 0, meaning the determinant of A is not equal to 0. The rank of A is equal to n. The number of vectors that form a basis for A is equal to the number of vectors present. So it is a complete basis. The n rows of A are linearly independent and the n columns of A are linearly independent. So that's all for rank, nullity, and subspaces. So thank you everyone.